Thank you. First, I would like to thank Piotr and David for the invitation. I already spoke about this subject many times, and so a very small part of the audience has heard this 2 or 3 times. But on the other hand, I will emphasize new points which were related to question of the physicist Grebenkov, with whom I have collaborated. Okay, so I start by reproducing the introduction written by Grebenkov, corresponding to some new motivation for the analysis of what we have done in the past. So we will consider new questions in the sense that the operator will be the same, but the condition at the boundary or at the interface, because in one case it's a transmission boundary problem, this type of condition appears in various problems of exchange. So molecular diffusion, heat transfer between 2 materials, transverse magnetization, and so on. So, and in this context, the operator which appears is quite simple. It's simply this Laplacian with some coefficient minus I gamma, which is a parameter, real parameter, J, which is another parameter, x1, so just one direction. And so in 1D, you recognize the so-called complex Airy operator, but the real physical problem here is at least in 2D or in 3D. Okay? And then we are interested with the corresponding evolution equation, and typically with the behavior of the associated semigroup to this operator. And then here I don't write the boundary condition, but everything will be so for most of the problem in some open set omega, and for the interface problem in the union of two open set. Okay, so and so in the first part of the talk, I will come back to this complex Airy operator that I have, for which I have presented many results in the past, because it appears also in many other physical problems like fluid dynamics, time-dependent Gans-Orlando problem, and so on. So, and so the first thing to recall is that this capital D corresponds to 1 over I d over dx. And so, and this, the spectral, so you can look at the spectral property of this operator. So first on the real line, and here it has this apparently strange property that the operator has compact resolvent but has empty spectrum. So this is a very simple example of operator with empty spectrum. And then for the boundary problem, we will meet the problem typically, for example, the Dirichlet problem in the half-line. In the past, this kind of problem has been analyzed in detail, and for example, for the Dirichlet situation, we know that the space generated by the eigenfunction is dense in L2 of R+, but there is no Riesz basis of eigenfunction. And finally, in this case, the decay of the associated semigroup has been analyzed in detail through the so-called Gerhardt-Pruss-Lack theorem. So there was some discussion yesterday with Rössler's talk about this thing. Now, in the context of nuclear magnetic resonance, there are a lot of contributions on the subject. And in particular, one can mention in the physical literature various papers where some spectral properties are analyzed. So in addition to the standard problem on the half line, I will add this transmission problem which occurs in this context. And so now you are on the line, but you have at 0 you have the interface, and you connect the left derivative and the right derivative of u, and then u prime of 0, which is the common value of u prime 0 plus and u prime 0 minus, is equal to kappa, the jump, u of 0 plus, minus u of 0 minus. So for the colleagues who are familiar with Schrödinger, with Dirac potential, it's delta prime. The parameter kappa is in the physical problem is positive. So in the mathematical problem, you could also look at any value of kappa, but the fact to assume that it's positive simplifies a little the discussion. Now, you have two limiting cases. The case kappa equals 0, which corresponds to two independent Neumann problems on the positive line, half line, or the negative half line. And the limiting case kappa tends to plus infinity, which can be understood as no barrier at all. And so this is the problem on the line. Okay. Now here, so of course you have a lot of different results corresponding to the different situation, but I just write the solution, the results we get for this transmission case. And so for the transmission case, we get, because kappa is positive, the contracting property, we get a discrete spectrum. And more difficult to show is that the eigenvalues are simple, and they are determined actually explicitly by the solution of this equation. So AI is the Airy function, and so this corresponds to AI prime is the derivative of the Airy function. So the Airy function, I will come back later to this, is an entire function. And so this equation is well defined. So what can we see is that for kappa equals 0, we recover what I said about the decoupling with two independent Neumann problem with the 0 of AI exponential 2 pi I over 3 lambda and the conjugate solution. We recover Neumann as. So for all kappa positive, you can localize, at least for n large, the eigenvalue in the neighborhood of the eigenvalue that you find for the Neumann problem. So of course, for kappa small, you can think it's just the perturbation of Neumann. But for n large, this looks like the perturbation of two independent Neumann problems. And finally, and this question was more difficult to get, and this is one of the motivations for some of the results I will present later. The space generated by the eigenfunction of the complex Airy operator is dense. So I can write L2 of R or L2 of R minus times L2 of R plus for this transmission problem. Okay. So here is the picture of the so-called epsilon pseudospectrum, which was discussed already yesterday. And I recall that what you are putting on the picture are in red the spectrum, and the black lines corresponds to level sets of the norm of the resolvent. And so you see a structure which is symmetric with respect to lambda gives lambda bar, and so there is a reason for that. You see a zone here which can look mysterious, but which will be interesting to analyze later on. You see also this vertical line, which can be explained by the properties of the level set of the free resolvent on the line. And so this does not look like the picture of yesterday for the cubic, for the model minus dx squared plus ix cubed plus cx squared, where the lines were going on the left. And so for this kind of model, you can hope that the decay of the associated semigroup is given by the smallest real part. Okay. So I recall very briefly the basic properties of the Airy function. So this is a solution of dx squared plus xu equals 0, so the real Airy function. We have a lot of information about the zeros of the Airy function, or the zeros of the derivative of the Airy function, which are intertwined with the zeros of AI. And then in order to look at our complex Airy operator, we have to make some complex rotation of 2 pi over 3. And there are two basic relations which are quite helpful. So the Wronskian relation, expressing the fact that you have two independent solutions of the equation W, this one, and also another identity which is quite helpful and maybe not so well known, which relates AI of z, AI of exponential minus alpha z, and this one. So it's clear that we have three solutions of the Airy equation, so we have to, it should be a linear relation between the three, because the dimension of the space is 2. But this is very explicit. Okay, and so you have expansion at infinity in suitable sectors. Okay. Now I come back to the Dirichlet problem, because for understanding this transmission problem, I have first to learn more about the properties of the resolvent for the Dirichlet problem. And so we know explicitly how to describe the eigenvalues of this operator A plus, so on the half line, because this is immediately related to the zeros of the Airy function. So we have on the half line we have also compact resolvent, but we will need various estimates on the resolvent. So for the problem in L2 of R, so I have said that so there are no spectrums, so the resolvent is lambda gives A minus lambda minus 1 is holomorphic in the whole space, but the control of the resolvent in L2 in the norm here or in the Hilbert-Schmidt norm gives rise to a very precise control, but which is exploding as the real part of lambda tends to plus infinity. And there is this power, free half, which is quite related to the fact that the spectrum is empty. So I will not, I've explained this in many cases, in many talks, so I will go rather rapidly on this. And then I will look more carefully to this Dirichlet realization. So there are no problem to define the Dirichlet realization of this problem, which is accretive. And if you want to prove in the Dirichlet case the property that the eigenfunction form a complete set in L2 of R+, you can either use explicitly the form of the eigenfunction, which are translated from the Airy function, or you can try to have a more abstract approach for this, looking, for example, to a rather standard technique that, for example, you can find in the old book of Schmel-Agmon. And in this old book, I think it's in the 60s or beginning of the 70s, I don't know. What you know is that in order to prove completeness for the eigenfunction or the generalized eigenfunction, but we are in a case where there are no generalized eigenfunctions, so there are no Jordan blocks in this situation, we have to analyze the resolvent on suitable rays outside, suitable rays with some angle which is smaller than some quantity which is related to the Schatten class of the resolvent. And so in this situation with this operator, we know that we have separate regularity in the sense that if we are in the domain of the operator, we have U in H2, so the Sobolev space, and XU in L2, separately. And with these properties, it's very easy to determine the Schatten class for the resolvent. And so this resolvent is in a Schatten class for P free half. So at the level of the control of the resolvent on suitable rays, the rays should have an angle less than 2 pi over 3 in order to have the right control. And here it's easy to finish the proof because we have the control of the resolvent. So sorry, I will. We have the control outside the numerical range. And the numerical range is the quarter. And so the angle is pi over 2. So it's just enough to use the information about the resolvent outside the numerical range to get the completeness of the eigenfunction. Okay, I come back to the explicit form of the resolvent. So you can write it as the sum of two terms, one contribution corresponding to the free resolvent, for which I have already presented estimates, and the additional term corresponding to the boundary, which can be explicited as the product of two ions. Okay, so this resolvent is compact, and you get back the information that the spectrum is given by this value by looking here. This gives the pole of the resolvent. Okay. Sorry. Now, if you want to do the same for this transmission problem, then we have seen that we have the range. The operator behind is the x² plus ix, and so the range of the numerical range of the operator is the half space. And we have still this Schatten class Cp with P just as close as you want to free half. And so if you cannot, it's not sufficient to play with the numerical range. We need an estimate somewhere in the middle of the numerical range. And so it's natural to think that looking, so this is not very enlightening to look at the picture. Where was it? Oh, yes, here. It's not. So we imagine that maybe we can have a control of the resolvent on this line. So of course here we have two level sets. We see only two level sets. And so the idea is to try to prove an estimate for the resolvent in this region. So now we can compare the various resolvents for Dirichlet, Neumann, transmission problem. And what we can realize is that when we compare two resolvents, the difference on the real line decay more rapidly is in O of lambda minus 1. And so it's enough now to have a control of one of the problem for the resolvent for one of the problem. And this is why I come back to Dirichlet. And my question now is to control the resolvent on the real, positive real line for the Dirichlet problem. And so what is new here? What is new is that we are at the boundary of the numerical range. We are not outside. We are just at the boundary of the numerical range. Okay, let's continue, come back to here. Okay. And here, this is the estimate that we will establish along the boundary of this numerical range. So this is a problem which was looked at in the case where you have no boundary in the paper by Denker, Jostrand, and Zworsky to analyze what's going on near the numerical range. So this was done in a semi-classical context, but as far as we cannot apply directly the techniques. So the proof of this, so you see the decay is lambda minus 1/4 log lambda 1/2. So all the decay that I can measure for Neumann, for transmission problem, will be the same, because as I said, the difference is O lambda minus 1. So I have no time to detail the proof, just the starting point. So we choose to compute the Hilbert-Schmidt norm. And if you think of the estimate we have for the free resolvent, it increases like exponential real lambda to the power 3/2. So it increases a lot. So in order to show that it tends to 0, you can imagine that you should have a lot of cancellation. And it's not enough just to look at the main term in the asymptotic expansion, because if you don't find the right form where you see the cancellation, you will be lost. And so I don't remember, I kill almost everything in the, so here, the fact that we have this identity between AI of z, AI of exponential minus alpha z, and exponential plus I alpha z is quite important. And so after some playing with this identity, we get this expression for which we have already make apparent the cancellation. Okay, then there are 10 pages of computation to get the estimate. Okay, now the definition of the problem in the transmission case. So
In the Dirichlet case, the definition was very easy using Lax-Milgram. In the case with transmission, there is some difficulty because of the imaginary part is no more positive, but you have a positive part and negative part. So, but you would like to start with the same definition, but Lax-Milgram does not work. So you have no coercivity of the problem, of this problem with transmission. And but there is a trick which was already observed in a paper with Yanni Valmog, and we can also play by taking the scalar product with the sine of x and get estimates. So here is a version of a generalized version of the Lax-Milgram operator, which permits to define, similarly to Lax-Milgram, the operator for this situation with transmission. So I think Nicolas Raymond will speak about that, so I will escape. And so once we have done this, we can prove the same result as for Dirichlet, because now this proof, this abstract proof, which is related to the control along suitable rays, I have added the ray in the middle on the real line, and now I have again my 2 pi over 3. And so you get in this way that the set of eigenfunction is complete in L2 of R. The simplicity of the eigenvalues is obtained through a trick, so a rather short proof, but tricky. Okay, and so here is the result that you can obtain for this transmission problem. So yes, not so much time. So one observation which explains the picture where you have this symmetry lambda against lambda bar is that, the model, so you have some PT symmetry property for this transmission problem. That is, if you combine the complex conjugation with the map x gives minus x, you have the commutation of this operator with the operator as written here. No, not the commutation, because you go from plus to minus. Okay. Sorry. Yes, I think I can go to the second part. So the second part is to use all these estimates for the complex area operator to the real situation, which is a 2D situation. What we are doing is actually more general than just analyzing this model. Of course, I will consider a semi-classical problem, so this corresponds to a special regime for the parameter D and G. My domain will be fixed, so there are other questions where the domain is variable. So, but you assume that after some suitable dilation, you meet these things. So for this block-Torre model, V is simply x1. And so the question now is how to analyze in the semi-classical limit, that is h tends to 0, how to analyze the bottom of the spectrum, so it's not self-adjoint. So we are interested by the eigenvalues, if any, of smallest real part, and we hope through a Gerhardt-Prust type theorem that it's enough to understand the behavior of the corresponding semigroup. So that means that we not only want to localize the spectrum, but we need also to have estimate on the resolvent, say in the imaginary direction, because this is what we have seen yesterday. this is the control in the complex of the resolvent, which permit to determine the behavior of the semigroup. So, this dièse sharp, this sharp corresponds to Dirichlet, Neumann, Robin, transmission, exterior problem. So we have tried to find a notation which is suitable for any case. So if you just think it's Dirichlet, if you prefer. Okay, so here are the situations which are of interest. The omega bounded set with Dirichlet, Neumann, or Robin. The case of the so-called exterior problem. You take the complementary of the bounded set. The interface case, in the bounded case, so you have omega minus, omega plus, and you have a transmission at the interface between omega minus and omega plus. So say that, and then here a transmission problem with omega plus unbounded. And so all the results with suitable change in the statement at some point are okay. Okay, so all these problems correspond to specific boundary conditions. So Dirichlet, Neumann, this is Robin. So, and for simplicity, I put the sign on the Robin condition. So in this case, you have to be careful that for doing a semi-classical analysis, kappa should depend on H in a suitable way. So it's not, kappa cannot be fixed in this, but will depend on H. And here you have the 2D, or so the dimension could be 2 or more. You have this expression that the normal derivative is related to the jump along the boundary. Okay, so in the 1D case, as I explained before, you have this type of situation. Okay, so now what are the questions? First, define the operator. So when omega is bounded, there are no problem, but if there is an unbounded part, you could have a problem. Construct approximate eigenvalue. So mainly in this semi-classical context. Then, because it's a non-self-adjoint problem, it's to construct approximate eigenvalue does not mean immediately that you have spectrum close to this approximate eigenvalue. So you should work on this. You should at least see how the Casimodes are localized near certain boundary points, and possibly do numerical simulation. So these numerical simulations were done by Grebenkov. So when in the unbounded case, we need for the definition some relation of this type, relating the potential V and nabla V. So this is immediately true for V of x equal x1. But you see that there is already a problem. So we say V of x equal x squared minus y squared, for example, which is a case that we cannot avoid. Okay. So here is a statement about the construction of Casimodes. So you see that you choose a point at the boundary or at the interface for which nabla V. So nabla V different from 0 is the general assumption that we take, which is always satisfied for V equal x1. And here we take a point where a nabla V is perpendicular to the normal. And this is quite important. So these points are the important point in the semi-classical analysis. And then in this case, we can construct Casimodes, assuming some generic
generic condition about the second derivative of the restriction of V to the boundary at this point. And then you have a complete expansion, which is based on the two operators appear. This one, the Airy operator, with a different boundary condition, and the Davis operator, so the Schrödinger operator with magnetic, the Schrödinger operator with complex, so the complex I y squared. So these here are not toy models, so this is what you get, and this is what you have analyzed. So I have written here the problem in 2D. So if the dimensions is larger, you have more things. Okay, so there's a question with the sign here and here, because there are coefficients, and the difficulty can, special difficulty can occur when these two parameters are not the same sign. Okay, so I have 2 minutes left. Oh, a little more. 3. Okay, so I will now just present the second result, which is more than Quasimodo, but localization of the spectrum, and I will present this for the exterior problem. So this is the last thing we have done recently, because this was a question. So to analyze the exterior problem, we have condition at infinity. Here I assume that not only the first derivative is bounded, but the second derivative also. And so this works. The most simple example is to assume that V of x is like the Bloch-Torre operator outside the big ball. Then we assume that nabla V never vanish. And then you have this special point where nabla V is parallel to the normal derivative. Then you have the various operator. Here, so I speak exterior problem. So I have the half line, and the eigenvalues. Sorry, lambda star of J is the infimum of the real part of this. So J will be a parameter which will be the relation with the initial problem will be detailed. Okay. And then you have a special set here, which is the set which realize for all these points the infimum. So in the case with Dirichlet and Neumann, this could be presented more easily in this way. So you look to the infimum of this. Okay. Then you have a generic condition on the Hessian of the restriction of the V at the boundary. And then here is the kind of result that you can have. So first, this is an exterior problem, so it's not evident how is the spectrum. But if you think that the problem of the free operator as empty spectrum, and if you think of conservation of the essential spectrum, then at least under the condition that V of x equals Gx1 outside the ball, you can prove that there are no essential spectrum. So the only spectrum which could exist for this exterior problem is a discrete spectrum. And now, if you look, so here are the results. I can determine the bottom of the real part here explicitly by the analysis of the Airy function. So here you don't see the Davis operator, and then I can control the resolvent on a suitable axis. So as a consequence, I can control the decay of the semigroup. And okay, so this is a quite recent result. So 2 years ago, there were already results for Dirichlet and the bounded case by Henry or Almog-Henry, but there was a condition about the sign of the normal derivative and
the second derivative of the restriction of the potential at the boundary. And because if you look to the kind of model which are behind the proof, you have the area corresponding to the linear approximation of the problem at the boundary, and you have at the point where the normal derivative is parallel to the normal, you have a model of this type. And there was when J and this alpha J have not the same sign, this quantity is no more positive. And so this makes life much more difficult. Okay, so thank you.
So are there questions or comments? We have -1 minute for that. Yes, please.
Yeah.
How do the Casimodes behave near these special points of the
They are exponentially localized.
And they are oscillating?
Because the basic Casimode is the multiplication of the area function on the half-line, in the part which is decaying, times an eigenfunction of the complex Davis operator, which is exponential minus alpha x square with real part of alpha positive.
Okay, so they are really...
So this is very concentrated.
Okay, so if there are no more questions, we can thank Bernard again.